morning, friends. Today we will see some very important relations related to refractive index. In our previous class we have learned about refraction, refractive index, relative refractive index, when we have seen Snell's law, critical angle, total internal reflection. But without completing the relations related to refractive index, this will be incomplete. So I thought we'll take up on. There are questions like all these years or from the time when it started, birds always are able to catch fish. Why fish is not evolving out of it every time it gets caught by the bird? We'll answer such type of questions with these relations. Let's start. In our previous class, we have seen this relation about Snell's law, n1 sin I is equal to n2 sin R. Let's say there are two mediums with refractive indexes n1, n2. When light travels from one medium to another medium, you will see it is bending. This is angle of incidence I and this is angle of refraction R. Then the relation we make with Snell's law is this: n1 sin I is equal to n2 sin R. Sometimes this concept can be extended when there are series of mediums consecutively, just like this. Let us say there are around 5 mediums here. You can see n1, n2, n3, n4, n5. And when light is passing through these 5 mediums, you can see it is bending and it is making different angles. Then the relation we can write is n1 sin theta 1 is equal to n2 sin theta 2 is equal to n3 sin theta 3 is equal to n4 sin theta 4 is equal to n5 sin theta 5. This concept can be extended to n number of mediums arranged consecutively. Now we'll take on an example why we are learning this. Let us say the question is a light is passing through medium 1 to medium 4. This is how it is passing. The refractive indexes are given here: n0, n0 by 2, n0 by 6, n0 by 8. And this is the origin. From here the distance of each medium is given also. And the angles are given here: theta 1, theta 2, theta 3, theta 4. Right. Now the question is, for what angle of incidence the emergent ray from the fourth medium will actually not enter the fourth medium, it will graze the interface. I repeat the question again. For what angle of incidence the emergent ray from the interface of third and fourth medium will actually not emerge, will actually pass through the interface? So that is the question. That means light is not entering the fourth medium. Now how would you solve this? We can apply the concept of Snell's law for consecutive mediums. We can apply and we can write here. You can see this is refractive index of this is n0. Angle here is sin theta 1 is equal to refractive index n0 by 2, sin theta 2 is n0 by 6, sin theta 3. This is theta 3, and here you can see light ray grazes the interface. Here the angle of refraction is 90 degrees, so we can write here n0 by 8 sin 90. Now you can clearly see that these all are in relation equal to. That means I can equate these two, or I can equate these two, or I can equate these two also. So I would equate this one and this one because I know this value. Sin 90 value is 1. So n0 sin theta is equal to n0 by 8 sin 90. This value becomes 1. So n0 get cancelled. So here we are left out with sin theta 1 is equal to 1 by 8 to 1. Then theta 1 is equal to sin inverse 1 by 8. So we found out the answer. This is the angle of incidence for which the light does not emerge into the fourth medium, right? Friends, now we will see the concept of lateral displacement. What it means. Whenever light is passing through a rectangular glass slab, light undergoes refraction, and when we are watching light from one side of the glass slab, we feel it got shifted, it got displaced. Let's see pictorially what it is. So let us say there is a rectangular glass slab. Let us say its thickness is T and its refractive index is mu, or we can call it N. It's up to us, right? Let us say this is the incident ray, this is the normal. Let us say this is angle of incidence. Here, since this is a denser medium, light is bending towards the normal. Let us say this is angle of refraction R. So obviously this angle, this is the original path of the light which actually it should travel, but it actually bent. So this is the deviation I minus R. Okay, because if this is I, this total angle is I, and in that we remove this is I minus R. Okay. Then when once it reaches the second surface of the rectangular glass slab, again it undergoes refraction. Now this is called as emergence because it has come out of the rectangular glass slab. We call this as emergent ray, and this angle which you see, this is angle of emergence. We represent that with E, right? And this angle is called angle of emergence. Let me tell you some important features of this. Remember that this incident ray and emergent ray will be parallel if this is a rectangular glass slab. And second point is, you can see the angle of incidence and angle of emergence both will be equal. So these 2 points to be remembered. One is the incident ray and the emergent ray will be parallel. Secondly, the angle of incidence and angle of emergence will be equal. Okay, right. Now we are interested in knowing the lateral displacement. Means the original path of the light is actually expected to be in this way, but finally when it emerged, we have seen light coming out, it shifted from its original path by some distance. Let us call that as x. We are calling this x as lateral displacement or lateral shift. When we are doing an experiment in a lab, for 10th class there is an experiment in lab activity. So there you will actually keep two pins here, two L pins on this side of the rectangular glass slab, and you are asked to look those pins from the other side. When you are watching, you will not see these pins somewhere in this way. You will see those pins being here like this. So that means the light got shifted, it shifted its path. We call that as lateral displacement. We'll try to derive some relations between the thickness of the glass slab and the angle of incidence, angle of refraction, right? We'll see those relations. Now you observe the figure carefully. From the figure, from this triangle BCE, you can just see here this is a right angle triangle. So from this triangle I can write sine I minus R is equal to, opposite is CE by hypotenuse is BC. CE is nothing but x, so I will write sine I minus R is equal to x by BC. Similarly, from the triangle BFC, from this triangle I can write cos R. Cos R is adjacent by hypotenuse. Adjacent is nothing but the thickness. So you can see here from triangle BFC, cos R is equal to, adjacent is BF by BC. Since we know BF is the thickness of the glass slab, cos R is equal to T by BC. From both of these, I can derive the relation for BC. BC is equal to x by sine I minus r, and here BC is equal to d by cos r. Okay, equating these two relations, we will get x by sine I minus r is equal to d by cos r. Right? Now from here, x is equal to t cos r sine I minus r. So this is the relation we finally made for lateral displacement. Right? Take an example. Let us say the thickness of glass slab is given 4 centimeter. Refractive index of this glass slab is √3 and angle of incidence is 60. This is given 60. So we have to find out the lateral displacement. Let us find out lateral displacement. We have T, we have I, we have to find out R value. How do you find this R value? We'll use Snell's law for it. Snell's law say that mu is equal to sine I by sine R. Mu is given √3, I value is given 60, sine 60 by sine R. So √3, sine 60 value is √3 by 2 sine R. We get cancelled. So sine R is equal to 1 by 2. Then R is 30. So we got the angle of refraction value 30. Let us try to derive thickness, the lateral displacement. X value, x is equal to T value, it's 4 sine minus 30 by cos R, that is cos 30. So you would get x value 4 by √3. This is the lateral displacement. Friends, now we will learn about the relation between velocity, refractive index and wavelength. We know this relation, refractive index is equal to C by V, velocity of light in vacuum by velocity of light in medium. We also know the formula of velocity in a medium is given by frequency into lambda. This we have learned in class 9 in lesson sound, which is also applicable to electromagnetic waves, that is light. Right. If we use this formula here, N is equal to C, in the place of V, we substitute this. Remember people, when light is traveling from one medium to another medium, we know that frequency does not change. This is very important concept. You all must remember that when light is traveling from one medium to another medium, its speed changes or wavelength changes, but the frequency remains same. Why? That is, let us say this is an interface of two mediums. Let us say light ray is traveling with a frequency 10 Hertz. That means 10 waves per second. Okay, 10 waves. After crossing this interface, 10 waves would come out. In this interface, nothing can happen so that some of the waves might miss. Just like 10 students are passing through a door. How many will enter the door? Those many will leave the door. In between, at the door, cannot disappear suddenly. Same thing happens with waves also. When 10 waves enter, 10 waves leave. That means frequency does not change. Okay. In case frequency does not change, then the only variable which we have is lambda. So now we have a relation n inversely proportional to lambda. We got a new relation between refractive index and wavelength of light. which also means that different colors will undergo refraction differently. When light is passing through any glass, red light will undergo refraction in a different way and violet will undergo refraction in a different way. This is what it means. Material might be same, but the refractive index for each color will be different. That is what this relation is telling us, right? I can extend this relation this way, that we know this is one relation, we have a relation this also. So we can write N1 by N2 is equal to V2 by V1 is equal to lambda 2 by. These are the relations which we can extend for two mediums. Right. Well, we'll move on to the next concept, that is real depth and apparent depth. We know because of refraction, sometimes we are confused about the depths of the water. We'll take an example here and we will derive a small formula. Let us say here there is some water inside a tumbler and we place the coin. Let us say the real depth of this coin is capital H. The person who is watching from outside, let us say we are watching from here, he will feel that it is actually raised because the light traveling from the coin is actually bending, but we perceive that is actually coming from here. So we feel that this coin is raised. We call this as the shift. We call this as the shift, or it has come to this height. So this is the apparent, the small h which you see, that is the apparent depth. This is capital H is real depth and this is apparent depth, and this is shift. We call that as x. Now we'll derive small relation here. From Snell's law we can write mu is equal to sin I by sin R. Okay, you can see that it is air. So here the refractive index is 1, so we can write this relation sin I by sin R. Right, and we know that mu will be always greater than 1. So I can write this ratio capital H by small h. Why not small h by capital H? If I write small h by capital H, I know that this is smaller and this is bigger. So numerator is smaller, then mu value will be less than 1. So I cannot write small h by capital H. We have to write capital H by small h because this is bigger than this. And we know refractive index values of any medium is greater than 1. Right. So we are going with this formula, mu is equal to h by h. So if I want to calculate the shift, how would I calculate? X, this is equal to this minus this. So I would write here. So from this I can write h is equal to h by mu. The same thing I'll write here, capital H minus small h value is this. So I can write h 1 minus 1 by mu. So this is the shift we have. We can extend this concept to several mediums. Let us say, for example, there are different mediums and each medium is having some depth, and we place some object. Then object will be raised every time in each medium differently. So if we are asked what is the total apparent depth of the object, then we can write h is equal to h1 by u1 plus h2 by mu2 plus h3 by mu3. We can extend this concept to n number of mediums arranged consecutively. Similarly, if they ask what is the total shift, then we can write this h1 1 minus plus h3 right. I hope you understood. the total apparent shift. Then we extended the same formula to all the three mediums, we added, we got this formula. Friends, now we will see the concept of normal shift. Earlier we have learned about lateral shift or lateral displacement. Now this is vertical shift or normal shift. Both are same. So how do we understand? Let us say this is a rectangular glass slab of refractive index mu and thickness t. When we are watching from the other side, let us say we are watching from here. An object, let us say the object was here. The original place of object is here. But when we see the object from the other side, we feel actually this object is here. That means we have a shift here. We call that shift O dash as X. We call this as vertical shift, right? Because this is being slightly raised, just like how we see the floor of a swimming pool. We feel like it is raised a bit. Similarly, when we see an object through this rectangular glass slab, we feel that it is raised vertically. So we call this as vertical shift. It is given by this formula, x is equal to 1 minus 1 by mu whole of t. Okay, this is nothing but result of this. You can see we have just applied that concept here and we derived a formula, right? Then we'll move on now to the concept of real height and apparent height. Earlier we have learned the concept of real depth and apparent depth. There we are talking about depths when people are watching from outside the water. Now let us say somebody who is watching from inside. For example, a fish is watching a bird which is at certain height. A fish, let us say it is inside. Let us say originally the bird is here, but the fish feels the bird is actually here because the light which is coming from that bird is actually bending, and when it is bending, the fish feels it is actually somewhere here. The bird is actually here. So this is the apparent height and this is the real height. You can see real height is less than the apparent height, and the fish feel the bird is at greater height. That is the reason when the fish is watching the bird, it feels the bird is very far away from me, it cannot catch. But in reality it is very closer, and the bird comes, it catches very close. The fish feel it's traveling very far. The bird is traveling very fast. But in reality it is nothing but refraction. Let us derive a small formula here. You can see clearly here apparent height is more than real height. So I will write mu is equal to small h by capital H, because we know mu value cannot be less than 1. So I have to write a bigger value in the numerator, right? So this is the apparent height by real height. Now we can derive formula for apparent shift. How much it shifted? X is equal to small h minus capital H. Okay, from here I can write capital H is equal to h by mu, right? Or the other way of writing this, small h can be written as h mu. So I'll write here h mu minus h. So I got a relation here, mu minus 1. Friends, now we will learn relations of velocity and refractive index. Real velocity and apparent velocity means, let us say, and when the observer is outside the water. For example, there is a bird outside here. There is a bird here. Okay, observer. And there is a fish inside. Let's call that as O dash. When this bird is observing this fish, it actually feels this fish is traveling slower. The real velocity of fish is actually greater, but due to refraction, this bird feels this fish is traveling very slowly. That is the reason birds, they can easily catch the fish because they feel they are traveling very slowly and they are worth to catch it. They can easily catch it, right? So going with the formula, mu is equal to real velocity of fish by apparent velocity of fish, that is VR by VA. Then similarly, we can go on the contrary. We can see if the observer is inside water. For example, let us say there is a fish inside, the observer is here and it is trying to watch something outside. There is a fish and a bird. fish is watching the bird. Actually the bird is traveling very slowly, but this fish feel it is traveling very faster. That is what in the previous relations we have learned. The real height of the bird is actually less, but the apparent height is more. Means fish feel the bird is actually very far away, and when it catches it, fish realizes it traveled very fast. That means real velocity, apparent velocity of bird is more and real velocity of bird is very less, right? So going with that relation, mu is equal to VA by VR. Okay, right? This is about velocities. Then we will see, friends, now we will see a field of vision of a fish. Let us say inside the water body of refractive index mu there is a fish at a height h. Then if the question is at what angle does the fish watch the entire world outside the water, or if you would like to know what is the relation between height and the area of the circle which is formed by this cone through which the fish actually watches. Okay, let us say the fish is here at a depth h, and we know that any light which is traveling more than the critical angle or at critical angle, we know the light will graze the interface. On the contrary, the light which is actually passing through the interface will actually enter at an angle of critical angle and it will reach the fish. So going with this fact that all the light which is just, even the light which is coming along the interface will definitely go along the critical angle and it will reach fish. That means fish can watch the entire world outside with an angle 2c. Okay, and it is three-dimensional, so we can call it as a cone. Okay, it is watching the entire world outside within that cone, and the vertex angle of that cone will be 2c. You can clearly see the light coming from this interface coming at a critical angle, and here the light coming from interface coming at critical angle. So if this is C, then according to the alternate interior angles this also should be C. So C plus C, it is 2C, right? And we can also derive a relation. Since this is a cone, there will be a base which is circular and it will have some radius also, so we can find out that radius also. So radius of the circular base of the cone formed on the water surface is R is equal to H tan C. How I got this relation? Let us see that. So we know that sin C is equal to 1 by mu from Snell's law. When we apply Snell's law, N1 sin I is equal to N2 sin R. This is 1. Refractive index of air is 1. So N2 is equal to sin I by sin R. If the angle of incidence is 90 degree, if this is 90, the sin 90 value is 1. Then N value is what? 1 by sin R. Since R is equal to C here, so we got this relation N is equal to 1 by sin C. Then sin C is equal to 1 by mu or 1 by N. So in that case, let us consider right angle triangle. Sin C is equal to 1 by mu, opposite by hypotenuse. So we can get the adjacent using Pythagoras theorem. We can get this value of adjacent side as mu square minus 1. From this we can get tan C is equal to opposite by adjacent, that is 1 by square minus 1. Now we got the tan C value. Okay, so here tan C, you can see from this right angle triangle, tan C is opposite by adjacent. So that means tan C is equal to R by H. Then R is equal to H tan C. R is equal to H tan C. Tan C value we got. So it is tan C value is 1 by can remove this. So this is the value of R. We can find out the area of that base also. This is forming a circular base. We can find out the area also. Area of circular base given by A is equal to pi R square. Apply the R value here. We get pi h square